All right. Hello, hello, test. OK. Glad everyone could make it to the Sheraton. I did not know we had sessions here. And I guess crossing the street wasn't too bad. So thanks, everyone. Thanks to everyone for being here. This is Cosmos DB's Gremlin database session. We'll learn a few things about Graph database. And we have the honor to have 3 guests from some of our customer cases. They'll talk about their specific implementation on how they use Graph and how it brings value to their applications and their businesses. And yeah, so Luis Vasquez, I'm a program manager in Cosmos DB. I specifically overlook the Graph database part of it. And you can reach out to me via email, which is lbsq@microsoft.com, or by Twitter. If you're familiar with Cosmos DB, the team loves Twitter. Like we have our hierarchy based on how many followers everyone has, and like that defines our rewards. So please follow me. I need this. Just kidding. So yeah, so we'll get started because we have a lot of content, and we'll have a few minutes at the end for any Q&A that for any questions on either the general topic of Cosmos DB Gremlin API, which is the same as Graph API, or any of the specific implementations that we'll hear about from some of our customers who are here presenting. So my name is Luis. I'm originally from Mexico. I've been working at Microsoft for 6 years, 3 of them as an intern and 3 of them as a full-time employee. Previous experience that I've worked in Microsoft for, previous projects that I've worked on are SQL Server on Linux, so putting SQL Server in Unix platforms, as well as Docker containers, connectivity for Azure SQL database, and now ever since 2017, I've been working on Cosmos DB for Graph databases. I have some of the samples on Graph database and Cosmos DB at my GitHub, which is Luis Vasquez, is my first and last name, and you can connect with me on LinkedIn with that alias. So the main topic here is Azure Cosmos DB Gremlin API. How many people here have heard about Cosmos DB? Like, say, how many people here know about Cosmos DB? Like a level 100 understanding. OK. How many people here have implemented Cosmos DB in an application? Other than our customers, of course. Cool. So good 30% of the room. And him as well. OK. So I guess I don't have the need for the next slide, but here it is anyway. As you know, Cosmos DB has APIs on top, which you can use to talk with the database on any of the data formats in the middle, just to get all the benefits in the bottom. A couple announcements that we had to build were database shared throughput. So you can specify a level of throughput that will then be shared across all the collections within a specific database, multi-master replication, bulk import utilities, and much more. Now, for those of you who have used Cosmos DB, you're probably familiar with what an API is in Cosmos DB. An API is just an implementation of the wire transfer protocol in each one of the database flavors. So if you create an account, it will have a specific flavor, which can be MongoDB, it can be Gremlin API, which is the Graph API, Cassandra, or SQL API, which is the core framework for Cosmos DB. Used to be known as Document DB. So there's some confusion all the time. We always get questions in the booth like, is this DocDB? Does it support DocDB? Is DocDB dead? Well, DocDB is now Cosmos DB, just one of the subsets of the services that it offers. Assuming that all the functionality that you need in your open source database model, as well as your client being supported on our side, theoretically you can have your database, your application, and your driver for your application just change the connection string to Cosmos DB, and it would work against a previously existing MongoDB API or previously existing Gremlin database. So we rely a lot on open source connectivity and a lot of the community contributions on the frameworks that work against Cosmos DB to make it easy to just use whatever platform of your choice, like programming platform or frameworks of your choice against Cosmos DB, and just enjoy all of the benefits that include like elastic throughput and SLAs and all of the global distribution part as well. So this makes every service unique in the sense that, well, there isn't a MongoDB service, managed service that handles global distribution, that handles elastic scale out, et cetera, or automatic partitioning. Is the sound OK? Is there? OK. So in a sense, you could perceive every single one of the APIs as a separate service of its own with all of the core benefits that Cosmos DB overall provides. Let's talk about Graph Database. So Graph Database is not really a new concept. It's been around for a while. Some of the bigger proponents of Graph Database include Neo4j, TitanDB, et cetera. And there's a lot of flavors around it. This article I like to share a lot. It's just, it's kind of old, but back in 2014, it says that Forrester predicted that 25% of enterprises would be using graph databases by 2017, and we have seen an explosion in graph user scenarios that involve just things around predictions, recommendation engines, just like exploration of different types of metadata on top of existing solutions, as well as the graph database being the main database engine solution on its own. So I recommend reading this just for some inspiration of what use cases can be achieved with a graph database. But that begs the question, well, what is a graph database? How many people here have used graph databases in the past? OK, good. So a good 30%. Let's see. Some of you know a graph database is just it's within the category of NoSQL or non-relational databases. And it just means that it's schemaless. One of the properties that defines it as a schemaless database is the fact that once you insert the data, you don't define a schema or a constraint on the data as you insert it. You define it as you read the data. So once you read the data, you'll define what kind of properties you want specifically. And that's going to infer what it means, what is the structure of the data itself. This is applicable to many other schemaless databases, including document databases like MongoDB or SQL API, et cetera. The one specific thing about graph databases is that it's optimized for processing highly connected data and just calculating relationships and operating on that end. So we talked about how there are many graph database standards that are defined today in many of the on-premise services. Cosmos DB Gremlin API is based on the Apache Tinkerpop graph standard. This is an open source standard maintained by Apache Tinkerpop and the community that comes with it. And it's between the two flavors of graph databases. This is known as the property graph. It has a couple of objects. Vertices represent objects. Edges represent relationships between objects. And all graph database objects can have an arbitrary list of key value properties that you can use to enrich the data set. We'll walk through a fun example on just how this plays out. And the fact that it's part of an open source standard means that there's an ample ecosystem of solutions, frameworks, samples, just all the goods that come with being an open source project. So as I mentioned, graph databases have been around ever since the early 2000s. And with Neo4j and Oracle, spatial and graph data types. The project, Apache Tinkerpop project, came up on 2009, and it's been developed ever since up to version 3.3.x and moving forward. Actually, Cosmos DB, the team in Cosmos DB, including myself and some of the engineers, are part of the contributors for the Apache Tinkerpop project. So we have constant discussions and sometimes arguments about how the project should move forward on how to stay aligned for providing enough functionality for people to use it against Cosmos DB, as well as for it to be a standard that will define the future of graph databases themselves. We added support for it, and it was in private preview ever since, I think, August 2017. And in January 2018, we actually released the general availability version of it. So today, Cosmos DB Gremlin API is the only graph database as a service, as a fully cloud-managed service, that is in general availability. There are other cloud graph database proponents which are not released yet, but Cosmos DB is still the only one that is out there. The popularity of Cosmos DB on its own made the graph database option go up to the second place, just underneath Neo4j. So this DB Engine's ranking is actually based on how popular the database is in terms of like Stack Overflow questions, in terms of GitHub contributions, in terms of job postings too, and other things like that define like if this database engine, like the one valuable conclusion that you get out of it is that if this database engine is going to continue existing based on its demand and the community that's built around it. So as I mentioned, all the Cosmos DB features are available through this. And it's fully managed, horizontally scalable through partitioning, and it has support for some of the major programming platforms, including the ones listed below. So we'll talk about what makes a Tinkerpop graph database and how you can use it to model objects. And I like to say that this example is usually the only thing you need to know about Tinkerpop graph databases to start using them in an actual solution. After that, we'll talk about some of the implementation patterns and some of the solutions you can build around it. So what is a Tinkerpop graph? What is a Tinkerpop graph? There's two objects, vertices and edges. Best practices include having an ID. Having an ID is necessary, but best practices include using the label as the type of object that you're defining. So, for example, if you have a graph object named Luis, well, it is of type person. That is something you denote inside of the label property. Then it can have a list of multiple properties, as well as the edges. The edges, in this case, I got questions in the booth around what are the best practices for edges. Edges, you have to name them around the type of object that they, semantically, the type of object that they are targeting at, just so that the solution is scalable both in terms of syntax as well as it is scalable technologically. So we'll walk through a quick example on how to use a graph database. So assume the following graph. We have Kobe Bryant as one of the objects, and we'll enrich the data by adding a few of the properties that might be relevant when querying this data. You have a vertex of label person, and you have properties, age, and height. And then we can add another object that denotes that Kobe Bryant is part of the LA Lakers, right? So we have a label team, and a label is part of, which denotes that it's part of a team on that end. Now, to increase the data on this example, we have the fact that Kobe Bryant has won 5 NBA championships and the years that are denoted there, as well as in 2018, something pretty historical happened. Kobe Bryant was the first NBA star to actually win an Oscar. So the Edge Has Academy Award will point to the 2018 Oscar that he won for Best Animated Short Film. This is a pretty well-connected graph until you insert a vertex that's, for example, Tom Cruise. Tom Cruise, as you probably know, has not won an Oscar, nor has he won an NBA championship. It's far away from it. So, so how do we make this a connected graph? And just for the sake of data modeling, well, they're both connected because they are Hollywood celebrities, regardless of how many awards they've won. So this is an example of how you can use graph database to model real situations, regardless of what constraints you'd have on the data itself. Now, what about the scale? Partitioning is handled automatically in Cosmos DB, so the only detail that you have to take care of is adding a partitioning key if you create an unlimited collection. So as a lot of you know, there's two types of collections. One of them is fixed, which has a limit of 10 gigabytes in size, as well as 10,000 request units per second. Or you can have an unlimited collection, which does not have any size or throughput restrictions, and it can go up to millions of request units per second. So it can become a theoretically infinite data set, because every partition will now have those enforced, I guess, linear qualities of being 10 gigabytes in size and having 10,000 request units each. So all you need to define, this is something that's really complicated to handle in the back end, but it's done automatically. And all you need to define is a property of partitioning key on the vertices. A couple more details on that include the fact that in a traversal, there may be cases where you find a graph that is connected across two partitions. This is known as a cross-partition query, and it has the implication of having additional latency just because the two partitions have to be scanned such that the connection can be found between these partitions. So what we do to optimize that is we automatically co-locate the vertices and their outgoing edges in the same partition, so you only have to care about the partition key on the vertices themselves. So when should I use a graph database? Well, if you're coming from the relational world, a graph database usually solves some of the pains that are found just by the fact that relationships are denoted as just an additional data element as opposed to a constraint or as opposed to a connection between a bunch of tables. So if you have hierarchically structured data, meaning multiple parent hierarchies on the same table, on the same rows, you may benefit from using a graph database. If you have self-referencing tables in relational databases, or the case of groups or groups, and then n numbers of hierarchies on top of that, maybe a graph could be a better solution. Overly complicated design or queries, like if your queries have like a couple more joins, like say 80% of the lines in a query are joins, then probably your queries are exploring more relationships than they are exploring data inside of the table itself. And just flexibility in the data model. Just like how we inserted a Tom Cruise vertex on an awards graph, that could mean that any kind of business pivoting that would require modifying the data set can be supported. That was a joke. So there are no constraints on adding new data. So you collect data first, run queries later. So is your data naturally a graph? Well, we'll talk about a very brief example. So on the left side of the screen, we have the relational implementation for this solution. And on the right side of the screen, there's the graph representation of it. So we have an HR data set, right? And things work out OK. There's 2 people under the sales group. There's 1 person under the engineering group, my manager, Rima. And what happens if, for example, in a company, kind of like Microsoft. Microsoft does this all the time. What if you say, OK, what if an employee can belong to multiple groups? So there's a sales and engineering group. Well, to implement it in a relational world, you'd have to create now a new table that denotes the relationships between the groups and the employees, and then map the fact that an additional employee can belong to different kinds of groups. So in this case, in the graph database world, you just add an additional relationship saying that, OK, an engineering group now also contains Andrew. Relationships are just documents. And what about nested groups? So in this case, we have to add support for adding Azure on top of the sales group and engineering group. So for this, I only worked in SQL Server for 2 years, so you might have a better solution for this in the relational world. For this, what I did was I extended the employee and group relationship table, and I added a groups or groups table, which is in the bottom, which is a total addition of 1 table, 6 rows, and 2 new columns, where in this case, we only have to add the vertex object of Azure and then 2 relationships. Heard there was some contest. No? OK. And again, this is just what I came up with if I was the developer, like the data architect for the solution. Let's complicate this a little more. What if we want to use this data to also store hierarchies of the employees? So who reports to whom, et cetera. So hierarchies, in this case, would be adding 2 documents on the graph side, just denoting the direct report relationship between Luis, Andrew, and Rima. But in the other case, we'd have to add an additional table just denoting for the same existing table how the relationships happen inside of it. I see a few nods, a few weird looks. There might be better solutions. This is just another caveat. This is just what I came up with. So once we have this data structure, let's see what it would take to add a new employee. So adding a new person here would mean that on the employees table, we have to add that row, and then we have to add all of the foreign key relationships for employee and group, and all the foreign key relationships between employee and ID, as well as the supergroup that is containing all of the groups. Whereas we can just add the new vertex and the 2 edges as part of the graph database solution. Now let's complicate this a little more. What if there's a super group, Microsoft? Microsoft owns Azure. Azure contains the 2 groups. This, on the left side of it, are the changes that you have to make to your data model on the relational world, whereas here, it only involves adding two more documents. So this is where graph database really shines. Just like whenever you have n degrees of hierarchies that contain existing objects, that's where graph database really does better in data design or data modeling. So here I just wanted to map out another situation where, as a person that has a Hispanic name, we also have our second last name as part of our names. And sometimes government-like forms require that. Sometimes they don't. So in this case, we'd have to add an additional column for second last name and keep it null for people who don't have second last names. Whereas here, I can only just add a property on the Luis object and include an additional thing, just like, bless you, it's like the additional schema changes that need to happen when the data of the elements themselves has to change. So let's look at what it would be to query this. And this was a bit of a challenge for both situations. So the query was, get all the managers under the same engineering group. On the left side, the query here means that get all the vertices, all the set of vertices, then filter them by the ID of engineering. So we'll get all the engineering group as the original data set that will then be exported. Then under engineering, go out and get all the members of the engineering group. So this data set will get everyone under the engineering group, which is Andrew, Rima, and the new person. Didn't bother to name it. And go in on the relationship of direct reports and get the name. So that will only get Rima as the manager of everyone under the engineering group. Now, on the right side, and again, this is the solution that I came up with, is basically I had to use a subquery inside of it to get the distinct employees that have reports. So you get the ID on the left side of the column that includes the relationships between the employees and their direct reports. And I do an inner join on the group just to filter it in the end by the name engineering. And so just a demonstration of how different solutions can be differently, they have different levels of complexity at the time of querying the data. So yeah, graphs are good for hierarchies. So a few implementation patterns are the following. What can you build with a graph database? So amongst the solutions that have been implemented on graph database, we have social networks, infrastructure monitoring as some of the, say, main solutions that are out there. There's also other things like knowledge graphs. We'll walk through a few examples on what this means. So if you have a graph that defines like a couple people and then how they belong to a group, common pattern in property graphs is a recommendation engine, and the recommendation engine is usually done by this method called triadic closure. So triadic closure is if Andrew and Luis both know Rima and they both belong to the Microsoft Soccer player teams, and chances are, and obviously this is an overly simplified example, chances are that Luis knows Andrew. If Luis belongs to the Microsoft Soccer players and purchased the Champions League TV package, and they know Andrew, and they have the same connections within a graph, and chances are that Andrew may also would purchase that. And this is only done through, again, just Gremlin queries, just queries that explore the relationships between each of these objects. In the case of a monitoring system, assume that you have different servers and different databases, and a hub that serves a traffic load balancer or whatever, that's not relevant, that serves the application to client applications. And assume one of these, I think I lost audio, no. And assume one of these databases dies, which would not be the case if you're using Cosmos DB, if you're still on-premise. But assume one of these databases dies. So a monitoring system that could be built around a graph database would be a system that looks like this. So we have different vertices denoting the databases, and then different edges connecting databases to the servers that that are being queried by these that query this database, and just different connections to whatever load balancer is on top of that. So in the metadata of it, we can have a property that says if a database is active or not, and then have a chain reaction on it saying, OK, well, if this database is under maintenance or data has been corrupted or something that makes it not be active, then you probably want to save on cloud resources and put that server to sleep. Or if you have like VM templates or something, you can kill that server and not pay for the time it takes for how long it is on. So that is just another of the solutions that can be built. And this, we have seen examples of this being implemented through just a monitoring system that uses change feed and Cosmos DB, and that with a system that is actually monitoring the actual resources and just storing all the metadata in a Cosmos DB graph database. The last example I wanted to talk about, theoretical example that I wanted to talk about, is a knowledge graph. And a knowledge graph is basically a combination of different data sets and mapping the relationships together to answer critical business questions. So it's not meant to be a transactional processing system, but more of a lightweight representation on top of it. And there are systems that actually run aggregations on existing transactional processing systems that then extract the metadata and then insert that into a graph database. And this can actually help you answer questions like, for example, out of the cities that are coastal and rainy, which of them claim fish and chips to be their main food? Disclaimer, all of them. All of them think their fish and chips are good. So other questions would be like, how many coastal cities are rainy? How many cities claim to have good fish and chips that are in Europe, et cetera? So there's a lot of, it's all about the data exploration that you can build on top of it by extracting metadata from existing systems. So for this, I would like to invite, we have, as I mentioned, we have a couple real use cases, real scenarios that are built on top of Graph Database. And I would like to invite Dave, who comes from Data Dynamics, and he will tell us about their use case today. Okay, I think it's on.
Hello, testing. Thank you. Thanks, Lewis.
Yeah.
So thank you for having me over for us to get this kicked off.
Anytime.
It's a genuine pleasure to be stood in front of you all. So Lewis has mentioned a couple of things I'd just like to call out here. So first of all, he's referenced Twitter. Now, there's an interesting story here. So we were having a little bit of an issue with some bulk insert in Cosmos a long, long, long time ago. And we actually connected with a chap called Denny, who may be in this room somewhere, who wrote us a very specific application that allowed us to bulk import our data in 20 minutes. This is terabytes of data, and it was taking 2 days before. So Twitter really does work with the Cosmos team, guys. Really does work. OK, so just moving on a little bit more swiftly here. So J2 Dynamics, who are we? We are the largest company in the automotive data space you've probably never heard of. We are the only global supplier of competitive analysis information or automotive intelligence to the car manufacturing industry. We have competition, obviously, within countries, within markets, but we're the only business that does this in a global context. So that's specifications around the equipment that you can have in vehicles, all sorts of stuff. We exist in, I just realized this slide is quite out of date. We're in 58 countries. We have over 600 staff. What we really do, our core business value, is that we allow our customers to make really smart decisions on their product proposition and pricing. And we do that today, and I'll talk through the story a little bit more in detail. We do that today in a very, I'm going to be generous and call it a megalithic context. It's megalithic. We have tons of infrastructure around people manually researching information, so it's all done manually today. We have hundreds and hundreds and hundreds of SQL databases, shuffling information around, ultimately generating the value that we provide to our customers. So in the context of where we are today and the context of where we're moving to, I think, as Lewis mentioned earlier, we have created a knowledge graph. So if you just flick on one slide. Thank you very much. So you look at the slide, and it seems to make an awful lot of sense, right? It's relatively common sense. BMW M5 has manual transmission and has a V6 engine. Now, the inference here is that if you have a manual transmission, you can't have an automatic transmission. You can't have both. Now, in a SQL context, where we've got tons of rules processing, data flowing everywhere, very, very manual activity, in a knowledge graph, we simply add another node, or vertex. Sorry, I'll use the correct terminology. We use a vertex and add an edge, which is can't have. And we establish a relationship between the two nodes that allows us to understand the differentiator between the two. Now, this allows us to do one very, very, very important thing for our business. We can correctly generate a 100% orderable vehicle in, I think it's about 3 or 4 milliseconds, which is a process today that we've optimized over 30 years and still takes about 2.5, 3 seconds, running in C++, highly optimized. So just by changing our paradigm from a transactional RDMS system, we've generated significant benefit for us and for our customers. So it's a huge benefit to us. I suppose that the other thing I should talk about on this slide is that the advantage to being able to simply add vertices and edges is that we're not constrained by a SQL data structure. So you guys in the room, I'm going to assume you know what Microsoft SQL is, so I'll just make some assumptions there. There is two ways to work with SQL, right? You can have a denormalized structure, which is very, very quick to query, but very, very cumbersome to maintain from a developer's perspective. Or you can have a normalized data structure, which is easy to amend, easy to extend, but when you come to query performance, it can be a real nightmare. So most businesses that I've ever worked in, and I've worked in a few that we've had these problems, solving that generally means you have to go and physically change your database schema to give you the flexibility. And that may meet your business needs for 12 months, 2 years, 3 years, whatever it may be. But the one thing you can guarantee in a traditional RDBMS is that that data structure will have to change again, and again, and again, constantly. Now, we were suffering quite badly with this problem in J2. We had normalized where we shouldn't. We had denormalized where we shouldn't. We had performance issues. Moving into this structure has given us some significant performance benefits, and I mean significant. But most importantly, it's enabled us to change our research taxonomy, our ontology, our lexicon, our data structure. So we have, the way we operate our research community is we research, I think it's about 3,500 data points for every vehicle that's on the market today, going back for 34, 35 years. All of that information is coded into what we call, annoyingly, schema. Right? It's the J2 schema. It's got nothing to do with the database structure, just what we call it. Moving into the graph data model has meant that we can change our schema at will with no impact to our downstream systems. So we add a new schema item, we start to research that new schema item. The only thing that needs to change is the consuming application can answer a different question. And the power that comes out of that, the insight that you can gain just by being able to make a simple change, right? Unbelievable. Generally, I would, if you're going down this road, I would definitely recommend that you invest as much time in your own taxonomies, ontologies, and lexicons before you start too much in the actual implementation perspective, because that's where you start to understand maybe not the depth of your data, but certainly the breadth of it. Right? And it's graph databases, particularly in a knowledge graph, are all about wide data, not big data. Mm-hmm. So move on to time. Thank you, Lewis. OK, so I've sort of talked to some of this slide already, but I think the takeaway from here is that simply adding a new vertex or a new edge means that you can generate completely new insights from existing information. Completely new. The way that we think about this is something like, really, again, going back to the BMW example, right? BMW has a professional media pack. Audi has a media pack, and I think they've got a business pack and something else. One of the more tedious tasks that we have to do in J2 from a research perspective is actually understand the contents of all of those things. That's how we provide the competitive insight back into our customer base, the manufacturers. Maintaining the links between those pieces of information and then generating the insight and the query against it, very, very complex in a relational database world, because you're tied to your schema. You're tied to your performance of your schema, and you're tied to your level of normalization or denormalization. In this context, you just add a new edge. You can link the two things directly. Right? The insight that you can gain from moving beyond just having structured rows of information and actually having linkage between different data sets. One of the things that J2 prides itself on is that we are able to go back 30 years and tell you from the very, very first Ford Fiesta, I think, Ford Escort, way, way, way back in the day. And for every single version of car that Ford has released up to now, we've got linkage. Now, we've got linkage in a graph context now because we've moved to a knowledge graph, but maintaining that linkage of information in a SQL database, those queries, some of those queries were nearly 4,500 lines long. Right? Now, nice. It's a single-line Gremlin query. Because linkage is, link your data together, particularly, again, knowledge graph context. Move on slide.
Yep. This is global distribution.
Excellent, thank you. So, one of the real problems with being a large, well, small but large global business is that you really want your data where your customers are. Now, all of our infrastructure today is hosted in West London. Lovely little place called Uxbridge. Don't visit. You're not missing anything. Now we have the capability to host our data in a single-click, replicated context in any region in the world. And I don't have to do anything. I tick, done. Tick, done. Untick, save some money. Right? It's brilliant. The level of capability, the flexibility, the resiliency that you gain from this, when you move away from being tied to physical pieces of infrastructure in data centers, or even in a SQL context where you have to maintain your availability zones, none of that exists in the Cosmos context. Right? It's very, very quick. So they say low latency reads and writes. I assure you, low latency is not doing it justice. Right? The reads and writes when you do your global replication is phenomenal. And this is on terabytes of data. We're not quite at the petabyte scale yet, but we're working on it. Tick on slide. Okay. So here's my this is my piece of insight that I want to share with you guys more than anything. The journey to moving from traditional SQL on-prem RDBMS context into Cosmos can seem very, very daunting. Where do you start? I think you can look at it in a number of different ways. So we've been on a journey with this. We started with Data Factory, and very quickly realized that it wasn't going to give us the performance we needed, and certainly not the cost point. The price was a little bit excessive when we ramped up for some significant demand. But if you think of the journey from SQL Server into Cosmos Database, the way that we've structured this is that we first of all have a staging format, which is the data lake. So we have an Azure data lake, and everything gets dumped in there in its raw native format. So we don't lose meta, right? Meta information is almost as valuable as information sometimes. And we take that information, we parse it, we process it, we normalize it, we do all the things you need to do with data to make sure it's clean and tidy, because if your data isn't clean and tidy, doesn't matter what you do with Cosmos, you're not going to get the results you want. So don't skip that step. You need to do that part. So we parse the information and we move it into a document database first. Seems strange, I say you say. Why would you do that? We use the document part for our localization. So everything we research is in what we call JATO English, which is really British English with a couple of American words here and there. It's mostly English. We're investigating at the minute using the tech services, some of the cognitive stuff, to automatically localize that for us, because why should we do it? I don't want to do it. Let's let machine learning take care of that. So we've built the document database there specifically for that purpose, to create what we call a standard data model. So that's all the facts for every vehicle, including all the options and all the other rules that sit between all the options on cars. And we then process the standard data model into the graph. And taking that approach, so that we've cleaned our data, normalized our data, and then put it into the graph, means that we know, because we've measured the processes, that we have 100% accuracy on the translation. Now, you'll see the little function symbol in the middle. Originally, as I said, we started looking at data factories for doing this because it seemed like the right tool, right? And it is the right tool. But for us, it was a little bit like using a sledgehammer to crack a walnut. Right? We didn't need that level of enterprise capability with what we're doing. So we rewrote the whole thing in this. I mean, this is really, really complex stuff, about 3 hours, into functions, Azure functions. And that's given us a major benefit in that we can process things on a trigger basis, and we're only paying for the import service into standard data model and into the graph database context when there is something to process. So the cost base, again, is definitely worth considering as you go through this process. The data migration has been a labor of love for us. But the most complicated part, nothing to do with the engineering, nothing to do with the implementation, actually been tidying our own database. 30 years of different interpretations of how we should research this versus this. We still have this issue today that some of our regions prefer to research in one particular context, so we've had to create specific functions to translate that and normalize it into one way. That's the thing that's taking the time for us, not the mechanics, right? So I think that's pretty much all I wanted to say.
Mm-hmm.
So I'll hand you back over to Lewis. I think we've got some Q&A at the end, so.
Yes. All right, thank you.
Thanks very much.
A hand for Dave. All right. All right, thanks, Dave. So our next guest here is Ramsey. He comes from the Microsoft supply chain, and he'll share a few details about the use case for supply chain. So,
thanks.
Yep.
So we produce first-party hardware like Xbox and Surface, and the nature of our data is very, very highly connected, and in some cases very hierarchical. So it turns out that graph database was the perfect solution to be able to get some deep insights. And one of our main goals is to always provide maximum value for our customers, and to make sure that we're always looking for ways to reduce costs, but to also improve quality and make sure that the level of service is really good. And in order to do that, you have to be able to get insights from cross-functional types of parts of the supply chain, whether it's manufacturing, sourcing, delivery, shipping, stores. We need to be able to find a way to cross-reference all that data. So we started thinking about, well, how do we get we have many, many different systems underneath that go across these functional areas, and we needed a way to say, we need it all in one place so that we can ask questions that could be various types of questions to enable our business to get these insights with the help of AI and machine learning to say, these are the opportunities. This one supplier is starting to look risky. Okay, now go find all the different parts in all the different devices that were produced by this supplier. So this is a very high-level type of architecture diagram. It represents what's happening in supply chain. You've got all these data producers on the left, our factories, our IoT devices. You've also got returns. There's a wealth of data of what are the parts that are constantly failing. And then that feeds back into enabling us to ask the questions to say, okay, this one part that keeps on failing, our testing, and we have to continuously repair, can you locate all the different suppliers that are giving us this part? Not only that, we just quarantined this part. Now we need to locate all the different devices that have this bad part in it. So now I can use the graph database to say, find me all the stores that have this device that includes this part, and find all the current devices that are being shipped, so they're en route, or they're with customers currently. So that took us about 4.5 days when we had to go across the different isolated, siloed systems. I think we're going to be able to get that down to minutes now. So on the right side, so this is kind of like a Lambda architecture. We're getting this real-time data streams, and we're going to fork it into two places. One is going to be the hot path operational stories. So stories is a key thing. And on the right side is going to be more the analytics and reporting. So that is very important still. It doesn't go away. We're going to take some information from the right side, like all the different predictive models, and say, okay, this is predicting that this one part is going to skyrocket in price, or this one supplier is starting to violate an ethical type of rules. Can you locate the different, based on what you're seeing on the right side predictive analytics, can you go and find the information on the left? And sometimes you just want to react to events that happen inside the environment. So, for instance, they just want to calculate the price of a bill of materials and be able to project what are the right suppliers for the parts. So this is an example. This is a very specific example that we started doing a POC for sourcing, and this is a bill of materials. And we had some very interesting discoveries, actually. There was a couple of eureka moments that we had, and we were just really blown away. So to price a bill of materials, right now in SQL database, it was taking around 3.5 minutes. And when we imported all the data, again, thanks to the Cosmos DB team with their bulk insert tool, we were able to quickly model this. So the thing I love about Azure is so plug and play, and you can really quickly get stuff up and running to prove out your POCs. This was done in about 2 to 3 days. And so what we quickly found out was what took about 3.5 minutes was now taking us under 2 seconds. It's that dramatic. So here's the design, and so it's not only the performance, but it's also how you model your data. What happens is that there's a program at the top that pins a root material, which is a Xbox or Surface or a pen even, and there's multiple parts to that device, and then there's also multiple suppliers. And what we started doing was that we're putting master data on the edges. You can do that, by the way. And that is one of the key things that helps performance. So you've got this database that's telling a story between the two vertices, and that's critical. To us, graph is a place that you can tell stories. What's happening? There's a relationship. Okay, tell me more about that relationship. So there's some kind of, I don't want to go too deep into this, but there's a split information, and it goes out months between these two parts. And the split just means I can use this part and have another alternative part that I can use inside this assembly. And then the same thing at the bottom, you have the supplier information. And for one part, we can source it from different suppliers. And then we have the breakdown of the cost and the split to say, oh yeah, 80% of this part is going to come from one supplier versus another. So what's going to happen now is that this is just about pricing, but we're going to start adding risk indicators about these suppliers. And we also have these audits that happen in our supplier areas. We go to their places and we look at a bunch of things. Are they being humane? Are they using the right types of standards? So that will also go into this information that's sitting there on the edge. And what we're going to do actually is that we're building this capability now where when you hover over one of these edges, you're going to get this line chart that's going to have this information that you can get instantly, where you need to do that previously with something like Power BI. Okay, so this is kind of the high level of what's going to happen. Data comes in. It could be from Event Grid real time, or it's coming from other services. We're pumping it into an intermediary stage, and then we have all these different functions that are acting as graph builders. They know the data, they know how it relates to other types of data, and it gets inserted into GraphDB. And then what's cool is that we've also thought about user experiences to say, hey, Gremlin is not exactly that easy to use. So we're training Lewis for people to just ask natural questions, and then we can extract entities from that, and then we can run the Gremlin queries for them. So somebody can say, hey, can you please price a BOM for this program for that material? And I have a demo. I don't know if it's going to work, but we'll give it a shot. Okay, so I think what I'll do now is I'll show you a quick demo.
Do you need help?
Yeah.
Okay.
So I'm just going to putting in a fake program, fake material. I'm not allowed to show it. So that was literally under 2 seconds. And now it's actually most of the time it's just building the tree. So this is an idea. This is actually like a pen. I'm just putting all the parts, I'm making them fake. But this is based on a real BOM, bill of materials. And you can see that it was super fast to build. And I'm just going to show you the query. That's pretty much it. Now we have a crazy recursive SQL thing that was taking us so much time. And what I'm doing in the back is that this is not just the hierarchy, but it's also some of the calculations. And now, so this is just the bill of materials, but not everything is costed. So I'm going to run a costing model now, and that will just bring me the parts that we actually pay for. So that's it. And so what happens is that we're invoking the functions app that has in it the SDK that talks to graph, and it also does the calculations on the fly. And now you can imagine that's, like I told you before, I said it took 4.5 days for them, 4.5 hours. 4.5 hours for them to get all the pricing for all the bombs. And now we've got, for one bomb, it's like under 2 seconds. Imagine now that we could horizontally scale all these serverless nodes and say, hey, calculate all the BOM pricing for us. It's going to take us minutes. And this is going to unblock business to start thinking about, oh, now that technology is no longer a constraint, what are the interesting things we can start doing now? Oh, let's start doing risk management. against our suppliers or other types of value-added business ideas. Okay, so now one last kind of usage. I'm going to try to do this Lewis thing. So I'm just going to look at the invocation. Part price calculator. Let's see if it's going to work. Ask part price calculator for program gold material brown. So that actually did work. I can't show you some of the names in there, but what it did, it extracted the entities using Lewis, and it went out and said, okay, I ran the same exact thing you're seeing on the screen, but we exported it to Excel. So now we're thinking of all these different ways that we can enhance our users' experiences through interconnected services. Thanks very much.
All right. All right, thanks, Ramsey. So as you have seen, we have explored two different scenarios completely separate and different industries. One of them is a bill of materials kind of mapping and calculations on top of that, as well as another scenario on intelligence gained from car data. So right now, allow me to invite onto this stage Glenn, who comes from Archive 360, to talk about another different scenario for graph database. So please welcome Glenn Luft. Okay. Let me actually switch it to your thing, which is on number 6.
What do you think?
There you go.
It works. Hello. Thanks for coming. Louise asked me here for 2 reasons. Why did we move to Cosmos DB, in particular the graph? And secondly, how? How are we using it? So a little bit about us. So Archive 360 is about information management and analytics. We manage customers' data, and we bring it into Azure. And we are a managed software as a service. We manage dashboards and reports out of mainframes, applications that are being sunsetted, live databases, CRM and ERP, enterprise resource planning, that are being captured for compliance reasons, but also for data mining, audio, video, images, SharePoint Online, SharePoint On-premise, and Office 365 emails. During ingestion, we have options of transforming the data, parsing the data, also analyzing for privacy violations, IP violations, quarantine that information. We also can anonymize that information. The data is stored in Azure Blob Storage, the metadata to Cosmos DB Graph. And Archive to Azure is our Azure application. The consumers of this information are the original application owner who wants to see that data according to the original view. So we have a style sheet that renders it back to that time as to how the end user viewed it. The compliance officer has the option of seeing that data as it changed throughout time. So we capture the information at each point, T0, 1, 2, 3, 4, and they can actually view it with the timeline viewer. Then we have the option of analysis BI based on Power BI dashboards and also our own reports and query interfaces against Cosmos Graph. This helps people who are not necessarily completely fluent in Gremlin.
Like me.
And last, but not least, there's the data scientists who love Gremlin and knock themselves out. Go for it. Good. For us, metadata is everything. So I'll give a kind of explanation on why. So this was us back in, well, I'm from the 1980s to date myself. So 1990s, we were working on basically archiving and information management of data out of mainframes, okay? And enterprise resource planning, not only a mainframe, but starting to get into the Unix systems and email. The customers had Oracle, they had Informix, they had, no DB2 then, but then SQL Server was kind of creeping its way in. And so we put our data in there, and it was good for rigid, and it was consistent. It's great for good performance to a limited sense. Then you hit about year 3, and you start hitting performance issues. Why? Because our data, our metadata, is by nature highly hierarchical. It is groups in groups. There are compound records, there are compound documents, and the way the users are constantly adding more metadata on the fly. The data by nature is heterogeneous. The metadata by nature is heterogeneous. Then, 2012, we looked at MongoDB. We started leveraging data warehouses. We started looking at Hadoop, and it's fantastic on performance, but you can see what was getting our customers, the price tag. And this is just an example of 1 terabyte of metadata in these 2 examples today. And that's our use case. Yours might be different. This is us on Cosmos DB. You can see the price point is much lower. We're able to handle hierarchies. We can do nested. I can do groups and groups. And it's elastic. I'm not putting all my metadata in Cosmos. Let's be clear. There's certain things that are still very well suited for SQL Server, for highly structured. We are a federated metadata model. I have some data in SQL that makes sense for a highly structured environment, but anything that relates to, I need hierarchies, I need groups, I need to add properties on the fly, I need to take away. In other words, anytime I see a lot of nulls, I immediately say, that probably didn't belong in SQL. It probably should go in one of the other 2. These are our customers today. What are they asking for? They want not just to query and manage information per data type. Let's say it originally was an email. They want to manage data across everything in our system, and that's across petabytes of information. They want to analyze. They want to reiterate on their classification. They want auto-classification. They want auto-anomaly detection, and in particular in the EU, GDPR. So they're hyperactively concerned about constantly looking for privacy information, flagging that, and immediately redacting it, either pseudo-anonymization or anonymization. Cosmos is helping me there because it's helping me give me clues as to where violations might show up. This is how we use it. We're basically doing user-to-information relationships. I'm doing information-to-information relationships, and of course, back up to the user. I have audit every single action that an end user does in our system is audit captured and maintained for the lifespan of the system. If that data is going to live for 30 years, that audit capture will live for 30 years. Privacy and security, the privacy and security in the example you'll see in the second example in particular. This is across billions of items. So to give you an example, a customer has 100,000 users. On average, for one data type, we see about 3 billion items out of them. That's just in year 1. We manage multiple data types, and they're all hierarchical, and they're all groups and groups. The first example at the top, where basically they want to do relationship mapping across disparate data, and they want one view to get to it and mine it. So that's it on the slide. I'll attempt a demo.
Do you need me to?
Yes, sorry.
Sure.
So, that's embarrassing.
Well, Scott Guthrie did it at the keynote. Did you see that?
No, all right. I just can't, no. All right. So this is Archived Azure. This is our front-end web application. And this is an example of the data. So I'm going to do a search. And I'm going to look for, we used, because I don't want to show any customer data, this is the old AdventureWorks SQL database. Yay, it still lives. Never dies. Here is that relationship view that I mentioned, okay? This is a user view. The end user had a special web UI, and we grab that style sheet, and we match it to this particular data, okay? So nice and simple. The end user also has the option of leveraging Power BI, so basically a tabular flattening of the graph database, and you can view, of course, pretty charts, and so on. Great, that's that. We built for our own use, but also our customers. Basically, is everyone here familiar with the Graph Explorer? A little bit? So it's highly extensible. I highly recommend you give it a try. So give an example. I'm going to walk through, for those people who have customers in finance departments, and that's useful to have because they have money, and I find that useful. So I'm going to go walk through an accounts payable three-way match. And that doesn't get any more exciting. So it's basically what this is there's a customer complaint. It comes to the finance department, and they want to see all the data and metadata relating to that complaint in one view. So this is an example. We also have that other view you saw, where you could search for it and see the same thing, but I thought I'd show it in graph. So it starts out with an end user there, and their last name is Laszlo, and they want to give us a purchase order. The purchase order, it comes from SAP ERP, and what this is going to do is it's going to basically do a link back to the system, and it's going to bring up a view. So the purchase order was brought into our system. As you can see, the credit card information was automatically anonymized. What I mean by anonymized is it was private key encrypted and the key was thrown away. If it was pseudo-anonymized, we would encrypt it and give someone the key. Okay, just to be clear on the differences there. Okay, so we got a purchase order. That's step one. Okay, the purchase order looked fine. Now I'm going to go to basically the sales order. This gets into the relationship mapping. What this is doing is it's a live lookup against the graph vertices and edges, and it's basically building on the fly this form. So this was a lookup against, let's see, the top sales order, that was vertices, then we have the customer, then we have each of the sales order details. You saw them in the Graph Explorer. Okay? There's also associated out of Salesforce, the opportunity itself. And again, rendered on the fly, and there is the opportunity. And then last but not least, you have some details about the account, again from Salesforce. So again, from input sources, we've taken it from an ERP system, from a CRM system, from the original AdventureWorks database, and so on. In this example, although it's not rendering right on the screen, there is a timeline view, and this shows each of the changes across time as the end user inputted it on the Salesforce account. And finally, you have the email of complaint. Which they wrote it in Spanish, and we leverage Azure, and we translate it. And that's my demo of how we leverage Graph across billions of items.
Thank you. Thanks, Glenn. Okay, so those are our demos and our guests for today. And we'll open this space for Q&A as well as any other, either on the specific implementations. We have some of our guests here to answer questions as well. And I can answer on other types of questions on Graph Database as well. So if there are any questions, there's a microphone in the middle of the room, or we can pass this microphone around as well.
Exactly working, but
Is it on?
I can talk about it.
Oh, wait, before you go, also remember to send the session evaluation. Thanks. Yes?
So the documentation on the emulator says that, it's not available for Graph.
The emulator is not available for Graph, and that is correct. Yeah.
So can I run this on-prem before I start racking up lots of cost in uploading data while I try it out and test it?
Right, so let me repeat the question. The question is there a way to run Cosmos DB Graph on-prem? And the emulator was an option to do that for Cosmos DB itself, the SQL API. Right. The answer for that is we are working on what we call a compute emulator, which is an emulator for all of the APIs. And it'll be coming soon. In the meantime, we suggest DB accounts for that.
So the short answer is no,
Yeah.
you have to actually start wrapping up Azure.
Exactly, that is correct. But there will be a compute emulator being released soon.
Do you have a timeline on
I don't work on that part specifically, but if you can send us a tweet, actually, we'll probably give you a better estimate. That's how it works. Yes.
Hi. Do you have examples of the bulk loader functions that everybody's showing? 'Cause that seems to be the key to this building, doing the bulk loading of the Graph DB.
Right. So bulk loading API is currently in preview right now. So we can add you to the preview. It's hosted on GitHub, and that provides a sample on how to use it. What kind of information were you hoping to get on the demo, on the
Just an example to see how it works and how to use it.
Right. Well, I can describe it since it hasn't been publicly released. I can't show that yet. Okay. It's in preview right now, but basically there's in the bulk, it's a library that sends out, instead of a single request at a time and a single document at a time, it makes a bulk operation of it and just uses a predefined Cosmos DB store procedure for that. So what you have to do in the application is you have to build both the logic for creating vertices and edges, as well as adding all the data that will be sent towards the endpoint.
I mean, is that being documented currently for us, for the general audience?
Not yet, since it hasn't been released in publicly yet.
So when's the public preview going to be open?
We expect that to be within end of month August, for that to be publicly available.
Okay. Thank you very much.
Thanks. All right. Are there any other questions? All right. Well, thanks for attending. I was hoping nobody would ask this, but there was, if anyone were to ask about SQL Server Graph versus Cosmos DB Graph, I had a slide ready for it. And if you want some, I'll just walk through it, because we have some time. SQL Server has a graph feature today, ever since SQL Server 2017, I think. And it's what we call a simulated graph. So it's a graph where you have to build tables for vertices and edges, and they introduced a new function in the T-SQL language, which is the match function, which will calculate all possible hops between two separate vertices. Now, this is best suited for if you have existing data in SQL database, either SQL database or SQL Server, and you on-premise, and you don't need complex graph calculations. So the examples that we saw before, where people used metadata from SQL Server and loaded it into Gremlin API, require additional complex graph calculations, including subgraph operations, traversal manipulations, etc. The main difference with Cosmos DB Gremlin API is that we implemented a open source graph standard. And so not only we have the functions that are defined by the graph community that are common graph scenarios, but we also have the existing platforms, the existing libraries that are open source that you can leverage towards it, as well as the flexible non-relational modeling, because in the end, the SQL Server Graph is a relational solution on top of it. Nobody asked it, but here it is. We're ready for that. Yes?
Tinkerpop will win out over Neo4j in the future?
Well, that's a great question. So the question is, and I couldn't hear the very last part, but I think I know where it's going. It's basically, Neo4j is a different standard. Do we see the Gremlin API implementing the Neo4j standard?
Yeah.
OK. So we are working with the Neo4j team. Do I have anything here that is private? OK. And we collaborated to create this Cypher to Gremlin translation library in conjunction with the Neo4j team. So yes and no. We don't have any current plans to support an open Cypher standard for this calendar year. But what we have is this library that has a very specific flavor for Cosmos DB. So if you search for Cosmos DB inside of this repository, you'll see that there's a decorator class that we helped define with the Neo4j team to create a more accurate translation of Cypher or Open Cypher to Gremlin. And this is available both in as a driver, so it's a shim that sits on top of any other Gremlin-enabled driver that will, or any other Cypher. It does translation back and forth. So that was a catch. But yeah, that is what is available today for support on Cypher workloads. Okay? Another question. So, if there are plans. Okay, so the question is, and I'll explain a little bit of the context around it. Drivers today, Gremlin drivers today support two different kinds of connections. One of them is the driver connection, and the other one is just sending raw strings to an endpoint. The second one is the one that is supported against Cosmos DB because there is a format, communication format in Gremlin called bytecode. Very deep dive into this, but there's a communication format called bytecode that we are working on getting support. So there is a plan to support bytecode, and the benefits for that include fluent API calls, as well as and just like support for additional drivers. As well as serialization benefits, will be there too. So we are working on a fix on fully supporting GraphSum v2, and that will be the baseline work for supporting bytecode drivers. Everyone's so obsessed with timeframes. It will be ready when it's ready. Just kidding. It's hard to tell. We have some additional priorities on top of that. We are building the bulk import library is our main priority for right now. Service stability fixes, as well as getting on top of the latest Azure Compute drivers. So for now, it's on the backlog. Sorry. Send us a tweet. Follow me on Twitter, then send a tweet. And okay. All right, well, I think that is all. Thanks for coming.